Okay, in this section we're going to continue on the limit, and we're going to learn how to evaluate limits algebraically. So in this particular section we're going to learn how to evaluate a limit using properties of limits, develop and use a strategy for finding limits, evaluate a limit using dividing out and rationalizing techniques, and last one will be evaluate the limit using the Squeeze Theorem. So first one, let's take a look at properties of limits. The limit of f of x as x approaches c does not depend on the value of f of x at x equals c. It may happen, however, that the limit is precisely f of c. Okay. In such case, limit could be evaluated by direct substitution. So this is one of the most important methods called direct substitution. You basically just replace x with whatever c value is, and you will find a limit. Substitute c for x. So in this case, limit when x approaches c of f of x equals f of c. So such well-behaved functions are continuous at c. So anytime you can use a direct substitution, that means the function is continuous. It's continuous at x equals c. Okay, so let's take a look at some basic properties of limits. Let b and c be real numbers, so the n be a positive integer. So limit when x approaches c for a constant b. So b is a constant. Limit of constant at any point will be the same constant. So the limit for x approaches c for linear equation x will become c. Limit for polynomial function with n degree, limit when x approaches c for x of n becomes c of n. Okay, those three are very basic limits, and it's very easy to understand. So for example, like limit when x approaches 2 for function 3 will be just 3. Limit when x approaches -4 for function x will be -4. So limit when x approaches 2 for x squared, here we replace x with 2. That's why we have 2 squared, and 2 squared is 4. So there are more properties of limits. Let b and c be real numbers, let n be a positive integer, and let f and g be function with foreign limits. So limit one for function f of x when x approaches c is L. Limit for function g of x when x approaches c equals k. Scalar multiple. So if you have a constant in front of f of x, then you can view this like you can factor out b in front of the constant. B times f of x. You can view that as b times limit. So the constant b goes in front f of x. Now we know limit of f of x is L, so it's b times L. That's why we have this result BL. And sum of differences. So when you can just separate the sum of difference as, let's say, sum of difference of two functions. Just separate into two limits. For for f of x minus limit x approach c for g of x plus minus g of x. Now we have L plus minus k. So this is like a quick proof of all these outcomes, right? And the product, the limit x approach c for f of x times g of x. You can separate into two different limit and multiply them times limit x approach c for g of x. Then it becomes L. Limit for f of x is L. Limit for g of x is k. So L times k. Similarly for quotient, right? You can just separate into two limit, one on top, one on bottom. So limit x approach c for f of x on top divided by limit x approach c for g of x, and it becomes L over k. Okay, that's simple. Exponents, you can just turn it like this. F of x to the n. You can do limit x approaches c for f of x. You can move the exponents outside of the limit. That becomes L to the nth power. Okay. So this is like a quick proof how all these basic properties of limits, but these properties are super useful. Okay, next take a look at this. We're gonna learn how to find a limit. As you can see, 4x squared plus 3 is a quadratic equation, so it's continuous everywhere, right? For any degree of polynomials. So you can do is limit x approaches 2, separate into two different parts of limit using the property number 2. You can put a coefficient in front using scatter multiple. You do x and put in a square. Plus limit x approaches 2, 3, right? So it becomes 4 times limit of f of x when x approaches 2 becomes, replace x2 with 2, it becomes 2 squared. The limit of a constant is that constant. It becomes 4 times 4 plus 3. So it's 16 plus 3, which gives us 19. Okay. So limit when as x approaches 2 of a polynomial function p of x equals 4x squared plus 3 is simply the value of p at x equals to 2. So using direct substitution method, replace x with 2 and then you end up with the result. So direct substitution property is valid for all polynomial and rational functions with non-zero denominators. So polynomials and rational functions, you can apply the direct substitution property, which is the simplest method you can ever have. So limit of a polynomial and rational functions. If p is a polynomial function, c is a real number, then limit when x approaches c for function p of x is equals to p of c. Replace x with c. If I is a rational function given by Rx equals Px over Qx, and C is a real number such that Qc not equal to 0, then limit for R of x equals to R of C. So replace x with C here. Replace x with C here. So it becomes Pc over Qc. So let's find the limit of this rational function. As you can see, we can do the direct substitution, so we can separate into two different limits, one on top, one on bottom. Since now both of them are polynomial functions. So you can do direct substitution, 1 squared plus 1 plus 2 on top, and 1 plus 1 bottom. It becomes 4 over 2, that becomes 2. So limit for this particular limit is 2. Okay. So let's take a look at the limit of a function involving a radical. N be a positive integer, the following limit is valid for all c if n is odd. And it's valid for c is greater than 0 if n is even. So for even radicals, the whatever number under radical must be positive. Okay. So I have this. Replace x with c. Limit of composite functions. If f of g, f and g are functions such as the limit for g of x when x approaches c is L, limit for f of x when x approaches L is f of L, the limit of f of g of x becomes f of limit of g of x when x approaches c. And since this limit is, this part becomes L, then we have f of L. Okay, so limit of composite function. So limit x approaches 0 equals to 4. Limit for radical of x, and we replace x with 4, you get the radical of 4 becomes 2. So limit of composite function, radical of x squared plus 4, is just equals to radical of 4, it becomes 2. So similarly, this is another example of composite functions. So limit of 2x squared minus 10 when x approaches 3, you're using direct substitution, replace x with 3. So it becomes 2 times 3 squared minus 10, it becomes 8. And limit when x approaches 8 for cubic root of x becomes cubic root of 8, it becomes 2. So now the limit when x approaches 3 for cubic root of 2x squared minus 10, since this is equal to 8, this whole thing, then we have cubic root of 8 gives 2. Limit of trigonometric functions. Let c be a real number in the domain of given trigonometric functions. So limit of sine of x when x approaches c becomes sine of c, because sine is a continuous function. Limit of cosine x when x approaches c becomes cosine c. Limit of tangent x when x approaches c becomes tangent c. Limit of cotangent x when x approaches c becomes cotangent c. Limit of secant x when x approaches c becomes secant c. Limit of cosecant x when x approaches c becomes cosecant c. So limit of tangent x when x approaches 0 becomes tangent 0. Replace x with 0. So get tangent 0 is 0. Limit of x times cosine x when x approaches pi, we can separate into two different limits. Limit of x when x approaches pi, limit of cosine x when x approaches pi. So limit of x when x approaches pi is pi. Limit of cosine x when x approaches pi becomes cosine pi. And cosine pi is -1. So it becomes pi times -1, it becomes -pi. So limit of sine x squared when x approaches 0, you could just write it as limit x approaches 0 for sine x. I think this is probably easier to understand. And for limit for sine of x when x approaches 0 becomes sine 0 square. Sine 0 is 0, 0 square becomes 0. Okay. So let's take a look at a very useful strategy for finding limit. So function that agrees at all but at one point. Let C be a real number, but let f of x equals g of x for all x not equal to c in an open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists. So these two functions are equal except at x equals c. Right? So then the limit of f of x when x approaches c equals to limit of g of x when x approaches c. Okay, so let's take a look at this one. This particular function, if you look at it, actually we can factor the numerator, right? So it becomes x minus 1, x squared plus x plus 1. As you can see now, if you cancel that, now we have a new function, which is plus 1, x squared plus x plus 1. This function is exactly the same as that one, except when x equals to 1, right? So it's exactly the same as x cubed plus minus 1 over x minus 1, except when x equals to 1. Okay? Because for this original function, g of x, x cannot be equal to 1. So, but for the f of x, x could be equal to 1. So these two functions basically are equivalent, except at x equals 1. Now the limit of g of x becomes limit of f of x. So limit of f of x, which is x squared plus x plus 1. Now since it's a second degree polynomial function, we can do direct substitution. So it becomes 1 squared plus 1 plus 1 give us 3. So limit when x approaches 1 for x cubed minus 1 over x minus 1 is equal to 3. So this is basically the graphical interpretation of the previous example. As you can see, this is function x cubed minus 1 over x minus 1. So it's undefined at x equals to 1. So that's whole there, this is whole, meaning undefined point. But for x squared plus x plus 1 is defined everywhere. So the only difference is at this point, as you can see. This one is a whole, this one is a solid dot, right? So these two functions are equivalent except x equals to 1. So they have the same limit at when x approaches 1. Because limit x approaches 1 for g of x exists, you can apply theorem 1.7 to conclude that f and g have the same limit at x equals to 1. That's a conclusion from the previous example. So factor the numerator, then dividing out like factors, cancel like terms on both top and bottom. Then apply the direct substitution, then we get the answer. Okay. So that's how we end up with 3 as the final answer. Another strategy for finding limit, learn to recognize which limit could be evaluated by direct substitution. If the limit of f of x as x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f, meaning the two functions are identical except at one particular point x equals c. Then if you cancel the same factor on both top both numerator and denominator, then you can apply the direct substitution afterwards. Okay, so that's how this thing works. Right? Transform the function f of x into g of x, and after that apply the direct substitution. And you can graph it to check your conclusion whether or not it's correct. Okay, so let's take a look at dividing out and rationalizing techniques. We already covered dividing out techniques. Basically, it's just involving canceling dividing out techniques. Canceling the same factor on both numerator and denominator, and apply direct substitution. For example, like this one, limit x approaches -3. If you do direct substitution, you realize that the denominator becomes 0 because -3 plus 3 becomes 0. So you cannot do direct substitution immediately. However, you can factor the numerator using the quadratic factoring. So it becomes x plus 3, x minus 2 over x plus 3. Now you can see you have the same factor on both numerator and denominator, then we cancel that. Now we transform this function to this function. So now you have limit x approaches -3 for x minus 2. And this is a polynomial with first degree. So we do direct substitution, replace x with -3. So we get -3 minus 2 equals to -5. Okay, so the answer is -5. Okay, this is detailed workout of what we just go over. Eventually end up with the answer of -5. And then if you take a look at the graph, so for our function f of x equals to x squared minus x minus 6 plus x minus 6 over x plus 3, at the point -3, -5, that's a hole. So we can do a transformation into another function, transform into g of x, which is x minus 2. After that, it's x minus 2, which is basically a linear equation with a hole, right? Then we do the substitution, limit approaches -5 when x approaches -3. An expression such as 0 over 0 is called indeterminate form because you cannot determine the limit. When you try to evaluate a limit, encounter this form, remember that you must rewrite the fraction so that the new denominator does not have 0 in its limit. One way to do it is to dividing out like denominators. And the second way, this is first way. Second way is rationalizing the denominator or numerator. Okay. Let's take a look at it. Okay, this one involving rationalize the the numerator. So basically, in order to rationalize the numerator, you just gotta find out the conjugate, complex conjugate. The complex conjugate for the numerator will becomes x plus 1 minus plus 1. And then you multiply this term to both numerator and denominator. And now for the denominator, we have a difference of two squares, and then it becomes x approaches 0, square root of x plus 1 square minus 1 square. The denominator is x times square root of x plus 1 plus 1. Now the numerator becomes x plus 1 minus 1. The denominator stays as. We cancel 1. Now you can cancel the x, right? Now we have a limit x approaches 0, 1 over. Now the numerator becomes 1. Square root of x plus 1 plus 1. After that, we can do the direct substitution and replace x with 0. So we get a radical 0 plus 1 plus 1 becomes 1 over 2. So it becomes half. So limit at this particular case becomes half. Okay. There's detailed solutions. And the table, that this graph actually reinforces our conclusion that limit is half, right? This is half. Okay. And that's a graph of the function, of this function. You can also use in a table and create a table like that. As you can see, when x approaches 0 from left, limit approaches 0.5, and when x approaches 0 from the right, limit approaches 0.5. So that's why 0.5 half is the limit. The squeeze method theorem. Okay, next theorem concerns the limit of a function that is squeezed between two other functions, each of which has the same limit at a given x value. Okay, so we have a function g and function h, and f is somewhere between these two. So this is like a presetting for this particular squeeze theorem. So if h of x is less than equal to f of x and less or equal to g of x, for all x in the open interval, select 3 different layers, and g of x is on very top, f of x is in the middle, hx is in the bottom. Then limit when x approaches c for h of x equals to L equals to limit of g of x when x approaches c. The squeeze theorem is also called sandwich theorem. Basically, f of x is the sandwich. Contained by h of x and g of x. Okay, let's take a look at two special trigonometric limits. For limit when x approaches 0, for sine of x over x is 1. Okay, and the detailed proof will be proof using the L'Hopital rule. Later, right? We're going to prove this later using L'Hopital rule. And limit when x approaches 0 for 1 minus cosine x over x equal to 0. So those two are very special trigonometric limit. So let's find a limit for tangent x over x. So what you can do is we can do this. Tangent x we can write as sine x over cosine x times 1 over x. Let's switch x and cosine x, and now we have a limit x approaches 0 for sine x over x times 1 over cosine x. Right? So we have limit x approaches 0 for sine x over x. And from the previous slide, we know that limit of sine x over x is equals to 1, right? So this is basically 1 times limit for x approaches 0 for cosine x becomes 1 over cosine 0, and cosine 0 is 1. So it's 1 times 1 gives us 1. So the final answer is 1. Using a special limit. So this is the graph of tangent x over x. As you can see, when x approaches 0, then this is 1, 2, 3, and 4 is right here. Okay, then the limit of f of x as x approaches 0 is equal to 1.